Hi there, thank you very much for coming. My name is Mike Anderson. I'm Chief Scientist for the PTR Group. Who exactly is the PTR Group? Well, we were founded in 2000. We've been in the business of supporting Linux since then. We've got a lot of different areas of work that we get ourselves involved in. One of the major issues that we're working on right now is a space refueling arm for NASA, where we'll actually go up and grapple satellites, unscrew the filler cap, and then put new fuel in it. The only problem is that the fuel that these things use is very toxic, and you're basically launching a bomb, and then you're refueling the satellite in orbit. That's kind of an interesting problem. We do a lot of flight software, but where we're going to be talking about today is a lot of the issues we've run into recently with the Internet of Things. We do a lot of systems architecture and deployment work for the IoT, and that's largely because of our experience in the embedded space. One of the things we found out kind of in spades with the IoT, as you go to the various large IoT conferences around the world, you find out that the vast majority of those conferences are still occupied largely by suits, getting up on the stage and telling you about there's going to be a great market here someday, and they're all trying to still figure out exactly what that market is. Unfortunately, what really happens is sooner or later you actually have to do something technical. And because we focus on the technical piece of this puzzle, that's where we get involved in a lot of the IoT conferences, because people will ask us to come in and say, okay, you understand the technical piece, can you tell us what it is we're supposed to be building? So my background, about 39 years in the embedded space. I developed part of VxWorks back in the day. Of course, I teach a lot of classes on Linux device drivers, Android internals, porting Android and Linux over to new platforms. I am a first mentor for robotics team FRC number 116 out of Herndon High School. And of course, I speak at a number of different conferences, including Linux, this one, Embedded Linux Conference. I've been speaking here since 2007. I was just talking to Tim Bird yesterday, and he says that I'm probably the most prolific speaker at ELC, and in this particular case, I actually have 5 presentations between the 2 conferences here today in this 3-day block. Interesting, but nonetheless, very challenging. What we're going to talk about, we're going to talk a little bit about the thread group history up to this point, why we need another wireless standard, yet another wireless standard in messaging and everything, interoperability with some of the other standards that are out there, and then we'll look at the underlying communications approach and some of the existing implementations that are available to us, especially focusing on the Linux side of things. So the Thread Group was formed in 2014. They're a 501c nonprofit organization. They are an independent, vendor-neutral organization, a little over 213 members at this point. Interestingly enough, they say, well, it's open to everybody. And it is open to everybody as long as you have the money to pay to be a member of everybody. So if we take a look at the Thread Group, the affiliate members, the cheapest membership they have is about $2.5K a year. And of course, that has to be renewed every year. The actual sponsor membership started at $100K a year. So when we talk about it being an open organization, well, yes, it is open to all of those who have the money to join the organization. The Thread Group manages the delivery and the enabling of these solutions. And what we're really looking at here is we're looking at an organization, and this is kind of common if you look at all the IoT platforms that are out there right now. They're all about branding. They're all about trying to maintain the brand, make sure that everything is compatible. All the members who are a member of the group can then put their little logo, the Thread Group logo in this case, on their individual devices. And the consumer can then walk into a Best Buy or a Fry's or whatever happens to be your type of electronic store these days and say, oh, it has the Thread Group logo on it. And if it has the Thread Group logo on it, I know it'll be compatible with other devices from Thread Group. That's great. It does help with making sure that the consumer has less confusion about what's going on with the particular products they're buying. However, it does then lend itself to a little bit of issues associated with trying to make sure that it's compatible with other standards. Now, of course, you have standards like Apple's HomeKit. They're not compatible with anybody because they're Apple and they can do it and get by with it. But the rest of us, we have to have some level of compatibility at some point in time. And of course, we had the Birds of a Feather meeting last night between the All Seen Alliance and the IoTivity folks from the the OCF organization. And they're trying to figure out exactly how they can play with each other. And then, of course, you bring in the thread group, and that adds additional complications. And then the thread group doesn't seem to be cooperating with very many people at this point. I think they're still trying to figure out exactly what their branding is and how they're going to move forward. There is an all-members meeting of the thread group that's going to be, that happened already. That happened in March. So that was a couple of weeks ago in Redwood, California. The big thread group open house, which is where they're going to be trying to recruit lots of additional manufacturers, is going to be in Shanghai. That'll be the 10th of May. So they are kind of moving forward with the actual production of the standards and trying to get that information out into the hands of the developers. But at this point, they're focusing largely on the developers that are part of the committee, that is part of the thread group itself. Here we have a sample of some of the thread group members, quite a few of them out there. Obviously ARM, one of the major members, NXP, we have Samsung, Yale, Locks. So there's quite a few. And as we look at some of the other of the logos, we see companies like Digi, of course, very big in the 802.15.4 radio business. We'll see exactly why that is and why that's important here in just a moment. But you have quite a collection here, not only silicon manufacturers, hardware vendors, television and consumer electronics vendors, all these people trying to come together and figure out exactly how to make this Internet of Things actually behave. Do we actually need another wireless standard? And of course, the apparent answer is yes. That's simply because if you look at the standards that are out there right now, we see a lot of existing IoT radios. They're either Wi-Fi or Zigbee, or there's some sort of proprietary protocol. And the thread group had its own set of requirements that they wanted to work from. So they wanted to focus on the ability to have low power interfaces. They are focused on the consumer side of the Internet of Things. We don't see a lot of effort on any of those companies focusing on the industrial side of the Internet of Things. And as a consequence, if we understand that they're focused largely on the consumer side, we then can understand a lot of the decisions that they're making about how they're going to be interoperable with other devices. They wanted to have a resilient network. We'll talk a little bit more about what that means here in a moment. They wanted it to be IP-based, but you'll see that when we take a look at the radio they chose, having it be IP-based represents an interesting challenge given the size of the maximum transfer unit for 802.15.4 radios. They wanted an open protocol. Now, open protocol is kind of it's a nice buzzword, it's a nice thing to say. The reality is that the layer 2, 3 interfaces are in fact open. It's when you start getting to layer 4 and layer 5 of the protocol stack that things start getting a little wonky in terms of your availability to actually see what the standard looks like. Of course, they wanted it to be secure, so we'll talk a little bit about the security of this thing as well. And now here we see the major one, which is fast time to market. Fast time to market in this particular space has a lot to do with what kind of radio you happen to be using and whether or not that radio is already certified by the FCC. So, or the whatever the Canadian version of that is, any of the communications organizations, basically they have their own standards. We need to be able to get it into a country, get it standardized, get it accepted, and then get our radio accepted as a potential transmitter, and then we can start selling product based on that radio. It has to be, along those lines, it has to be built on existing radio silicon. That means that we can't spend time to produce a brand new radio. It's very, very simple. They also wanted to make sure that they did not have any requirements for licensing of the radio spectrum. So by not licensing the radio spectrum, it pretty much dictates what spectrum they're going to be in, because there's only one worldwide radio spectrum that does not require licensing, and that's going to be the 2.4 gigahertz band. Unfortunately, the 2.4 gigahertz band has got a lot of stuff in it. It's got Wi-Fi, it's got Zigbee, it's got Bluetooth. There are a lot of competing things floating around in the 2.4 gigahertz spectrum. So we need to deal with that as well. So unfortunately, you could have said, well, why didn't they just use Wi-Fi? If they're interested in the 2.4 gigahertz spectrum, why not Wi-Fi? Their answer is actually twofold. First of all, they wanted to make sure that the vast majority of the sensors, and when we're talking about sensors in this case, we're really talking about things like smoke detectors and water detectors, moisture detectors for basements and things of that sort. They wanted it to be able to run for years on a coin cell battery. Typical 2032 3.3 volt coin cell battery, they wanted it to have at least 5 to 10 years worth of runtime on that. And you're not going to get there if you're using Wi-Fi. Wi-Fi at this point in time, with a given Wi-Fi standards that we have today, Wi-Fi just eats way too much power. It'd burn through a coin cell battery in about 20 seconds. So as a consequence now, we have not yet seen any of the stuff that's 802.11, I think it's the AH standard. There's another standard they're working on right now for a low-power Wi-Fi, and there's also one for a Wi-Fi mesh interface. Both of those are directly trying to compete against what the thread group actually chose as their underlying radio standard. Zigbee, of course, is relatively power efficient, but unfortunately, it's not an open standard. The Zigbee Alliance, if you want to produce something that uses Zigbee as a technology, then you have to pay your money to the Zigbee Alliance, and it has to go through the Zigbee Alliance testing process before you can put your Works with Zigbee logo on there. The Zigbee Alliance also has a major problem. There is Zigbee 1, Zigbee 2, Zigbee Pro, Zigbee IP, and all of them are mutually exclusive from each other. So in the Zigbee world, it is confusing to the customer. The consumer looks at it, he says, oh, it's Zigbee, but it turns out that he's got the wrong type of Zigbee, and therefore it is not compatible. As a consequence, this causes a lot of issue with just being able to use an existing standard like Zigbee in this kind of application. Zigbee IP is a slightly different standard. Now, if we look, Zigbee IP actually came out in March a couple of years ago. Zigbee IP is actually 6-low-pan. So if we understand exactly how the underlying mechanisms work, Zigbee IP is actually very, very close to what the thread group's standard looks like. So the Zigbee Alliance has just recently signed an agreement to collaborate with the thread group and bring the Zigbee library, the Zigbee cluster library, to sit on top of thread. And you'll understand how this works when we start looking at the actual layers that thread supports and where the Zigbee piece would then come into play. So Zigbee actually, for this Zigbee cluster library, we're really talking about layer 5, layer 6 kind of place, and it sits nicely on top of where thread stops. What do they mean by resilient? In this case, it can't have a single point of failure. And one of the major problems with Wi-Fi technologies is that if the Wi-Fi router goes down in the home, then you're basically out of business. There is no mechanism to fail over to another Wi-Fi router. As a consequence, we can't really use Wi-Fi as that particular standard simply because we needed to be able to make sure that in a location such as a home where we have lots of drywall and stud construction, we need to be able to A, get the messages around, and B, make sure that we can actually talk to the gateways, the border gateways, with a minimum amount of hassle. We also need to be able to support self-extending networks. Realize that in the consumer electronics space, when a typical consumer brings his device home, he might remember what his Wi-Fi password is. If you have any substantial sort of provisioning that has to be done for the device, this is going to be well beyond the capabilities of the typical consumer. So it has to be just absolutely dirt dumb simple for them to be able to provision the device, make it part of their network, extend their network, and then be able to control the device. Realize, of course, that if you're in the business of selling light bulbs, for instance, the consumer might buy 20 light bulbs at a time, and each one of those light bulbs then has to be provisioned so that he can actually take control over it and then control the color of the lights. If you have anything that's incredibly involved in terms of being able to provision that device, the consumer is not going to do it. It's going to be something that has to be really, really simple, really, really quick, and basically no more complex than taking the light bulb out of the box and making sure the light bulb is now part of your network. And in many cases, what we're seeing is a combination of technologies where we'll actually use NFC as a mechanism to be able to provision the light bulb while the light bulb is still in the box. And then when they take it out of the box, it will automatically be part of their network. But we also want to make sure that we have this requirement for being able to have some level of security. I don't want to be able to control, I don't want my neighbor to be able to control my lights from his house. That would, of course, be somewhat annoying, although it could be potentially humorous depending on how you did it. But in any case, we definitely want to make sure that we can be tolerant of interference. Now, this is another problem. When they pick the 2.4 gigahertz spectrum, they're, with all the other things that are there, now we have telephones, we have microwave ovens, we have all these other devices that work in that same spectrum. We need to make sure that when somebody's running the microwave, I don't lose contact with my light bulbs. So those are the kinds of things that they're trying to make sure that they can accomplish with this particular standard. It also has to be self-healing. So if I have a device who fails somewhere along the line, I can't have that device be the central coordinator. I can't have that device make, suddenly because it failed, my entire network is down. I now can't control the thermostat. So those are all important pieces that we have to understand about what their goals were for doing Thread. Of course, one of the other aspects that they're looking for is low latency. And if we take a look at some of the devices that we have out there, they're trying to make sure that their latency is on the order of 100 milliseconds for most transactions. So that's 1/10 of a second, and as far as most humans are concerned, that's essentially instantaneous. So the fact that there is a latency there, yes, we have to deal with the fact that we've got to come onto the radio, we've got to come onto the frequency, we've got to negotiate our PAN IDs and everything. But the reality is we want that to be reasonably fast. We don't want to have a lot of lag between what the user decides he's going to do and when the actual device makes that happen. We also will need to be able to scale this to 250 to 300 devices in the home. Remember, we're talking about light bulbs and thermostats and smoke alarms and other types of devices like that. Therefore, there's a good potential that there would be at least 50 to 100 of these devices in a typical home. So we need to make sure that we can easily extend the network without having to jump through a lot of hoops and not have to change the IP address range and things of that sort. The connectivity to the user interactive device. Now, this is another problem. Realize that most of these devices that we're talking about don't have user interfaces on them. So how do you set up the user interface for a light bulb? Well, it turns out that you have an application that then runs on either iPhone or Android or on either on a smartphone or a tablet, and these are referred to as GUI-ful devices. So the GUI-ful devices then have the option of dealing with the hardware and presenting a user interface that the user can hopefully deal with. The downside is there's no one app at this point. So each one of the manufacturers that are a member of the Thread group has their own app. So whether you're using the Big Ass Fans app for changing the fans in your house, or you're using the Philips app for changing the color of the light bulbs, those are two different apps. We know that they're compatible with each other because they're all members of the Thread group, but it still means that the user has to use more than one user interface in order to coordinate with a particular set of devices. So now the Thread standard itself, and when they put this out, they said, well, we want to make sure that we're completely standards-based. And that is a fine thing. And as an open source guy, I can completely support that approach. They wanted to build it on the existing 802.15.4 standard. So 802.15.4 is a mesh network. It's the layer 2, basically. We're seeing the layer 1 and layer 2, and then 802.15.4 stops. So 802.15.4 has several different MACs that it supports, or several different PHYs that it supports. The primary one is in the 2.4 gigahertz spectrum, so that certainly met the requirement of being able to be used internationally without having to do any licensing. But there are other PHYs that are available for 802.15.4. For instance, there's a sub-gigahertz PHY in the 915 megahertz band here in the United States. I think it's the 854 megahertz band in Europe. And what those bands do is they give us much longer distance. out of the 802.15.4.5s. There is, in fact, an example of this. If you understand what smart metering is all about, the advanced metering infrastructure, there are, in fact, a number of power meters that are available for the side of the house these days that all use 802.15.4 6-low pan in the 900 megahertz spectrum as a lossy mesh network. The advantage of that is it means that the power company can now read your meter without having to roll a truck. That's a good thing for the power company. What they don't tell you is there's a reverse path, so the power company can then shut the power off without having to roll a truck either. That may not necessarily be a problem until someone hacks that particular interface, and then when they do so, they can then start turning off power to large sections of the grid. That hasn't happened yet. Hopefully it won't happen, but we'll see. With 6-low pan, it focuses largely on, at least for this application, they're using UDP traffic over an IPv6 modification. So 6-low pan, we'll talk a little bit more about 6-low pan in a moment. It is basically IPv6 for low performance wide area networks, and that's where the 6-low pan comes from. It's basically nothing more than a firmware upgrade to an existing 802.15.4 radio. So this is a huge win. It means that we don't have to redesign the radios. If you ask a manufacturer, I was in China and asked a manufacturer, at what point does it make sense for me to make my own radio? And they go, 1 million units. If you're doing 1 million units, then it makes sense for you to make your own radio. Otherwise, you might as well just buy somebody else's radio that's already FCC approved. And therefore, if we take a look at where those radios are right now, we see Nordic Semiconductor, we see Dialog Semiconductor, we see folks like Microchip, there of course Texas Instruments, Freescale now has brought out a radio. All of these radios sit in the 2.4 gigahertz spectrum, and they all have the ability to be software defined. So in this particular type of an approach, it means we can have them run Bluetooth, low energy, we can have them run Bluetooth, we can have them run Zigbee, we can have them run 6-low pan, IEEE 802.15.4. We can have them do anything that sits in the 2.4 gigahertz spectrum. The antennas are pretty much the same because that's done based on the frequency that you're operating at. And all we need to do is to change the encoding of the signal, Gaussian frequency shift keying versus whatever other, OFDM in the case of Wi-Fi. So we really don't have to do a whole lot. If we get the radio approved by the FCC, we can change the software out on the radio with a minimum of hassle, and that gives us the ability to have relatively cheap, relatively available radio frequency equipment that we can then just start putting the thread group protocols on top of. Of course, what they are using for their security is they're using datagram transport layer security, DTLS. What this is being done, they're using this for several different things. First of all, DTLS is going to be from application to application. So rather than what we would typically expect to see with these kinds of devices sitting out at the edge, we would expect to see link encryption. Link encryption would be in the radio, and we would see an AES 128 type encryption in the radio. But there is another layer of encryption that they're actually laying on top of the thread standard, and that's DTLS. So DTLS is from application to application, not from radio to radio. So there is an extra layer here that's happening that will provide us a little bit more in terms of security. If we think about security, we have to think at least in terms of 3 elements: confidentiality, integrity, and authentication. So confidentiality is oftentimes by the consumer confused with the concept of privacy. Privacy and confidentiality are not the same thing, although they are slightly related to each other. As a consequence, we need to understand confidentiality simply means that nobody can read your data as it's transmitting across the air. Now, there is other issues associated with this. We have data in flight, which is the actual data in the message. We also have data at rest, which is going to be the encryption keys and the certificates and things of that sort. So there's a lot of things that have to play into this in order to make sure that all of this comes together from a confidentiality perspective. From an integrity perspective, we need to make sure that nobody can go in and modify the messages in flight. We don't want to have a man-in-the-middle attack. Your neighbor that you don't like buys a piece of equipment because he knows you're using similar frequencies, and then he starts inserting oddball messages into the network. trying to get your equipment to associate with him so that he can then modify all the messages. You said to make the light bulb slightly yellow and it becomes pink, or some other crazy thing like that that just drives you up the walls. So for harassment perspective, we also want to make sure that we have some level of integrity, guaranteeing that we don't have a circumstance where somebody has taken over our network. Also, authentication factors into that. We would like to make sure that whoever it is that's controlling the light bulbs is actually the person that's supposed to be controlling the light bulbs. Again, this all starts to boil down to certificates and things of that sort. Now, tomorrow I'll actually be talking in another session on how we go about securing embedded Linux, and we have to get into all of these issues of authentication, authorization, non-repudiation, confidentiality, integrity, et cetera, in order to be able to make some assertion that we actually have a secure system that could potentially stand up in court in case somebody decided to come after us because some hacker had shut something important down. The 802.15.4 physical layer is actually just the PHY and the MAC. So we're really talking about layer 1 and layer 2 of the protocol stacks. The upper layers are then left to other organizations. So 802.15.4, the IEEE standard, is deliberately defined to only worry about setting up the, having an address associated with the network and the actual physical radios. That as a standard, it actually supports several different topologies. We have a tree topology, we have a star topology, and a mesh topology. So when we're dealing with the mesh topology, I'm not sure why that decided to show up there. When we're dealing with the mesh topology, this is where we get the most flexibility out of the system. But unfortunately, as we're dealing with the mesh topology, trying to make sure that the mesh is self-healing then becomes a bit of an issue. Again, another one that we don't want to have a typical consumer have to deal with. So let's see if we can get this to turn there. There we go. So what are the limitations of an 802.15.4 frame? The frame itself is only 127 octets. So we also typically have a frame overhead of about 22 octets. So that gives us about 105 bytes with which we can do something. If we then add AES 128 encryption to it, which is the typical link encryption that we'll see on the radios, we lose another 21 bytes for the link encryption overhead. So that gives me 84 bytes for layer 3 and above. Now, if we were to look at standard IP style routing, we'd need to make sure that we had enough space in the header for the source and destination of the IP addresses. If we looked at an IPv4 header, IPv4 headers are roughly 20 bytes. It can be as much as 60 bytes, depending on additional extensions to the header. But in general, it's going to be about 20 bytes. Then we have an 8-octet UDP header, and that means we're coming up to about 76 octets minus the size of the source and destination addresses. So IPv4 addresses are 4 octets. They're 32 bits each. And if we then compare that to to IPv6, IPv6 addresses are 16 octets each. So they're 128 bytes for each, 128 bits rather for each one of those addresses. So if we have a source and a destination address for an IPv6 header, that's going to be 40 bytes in the IPv6 header. So that's a fairly significant chunk of the actual of the maximum transfer unit size that we have in 802.15.4. If we were to look at where Thread fits in this grand scheme of things, Thread defines only up to the layer 4 protocol. So we see that we have the 802.15.4 here in layer 1 and layer 2. Then we see 6LoWPAN setting on top of that. That's going to be our layer 3. We have distance vector routing. This is RIP. So for those of you who thought the RIP, Routing Information Protocol, was dead, gone, should never be resurrected, they've resurrected it. It is actually a flavor of RIP-NG, so it is RIP for IPv6. Then they have UDP and DTLS, so that's going to be the security piece of it for handling the user datagram protocol. And then Thread comes in on top of that. So Thread is an application layer. Now, Thread sits here. They've defined all these pieces. These are all standards, fortunately. And then there's a library that sits on top of this that enables you to actually join the personal area network, the PAN, and be able to associate with your close relatives. So there are a lot of examples of this. the multicast in the network, and this is, of course, with 6-LoWPAN, we do have the ability to do multicast. This means that our potential here is for doing discovery using MDNS. So just as we saw the other day with IoTivity using MDNS and universal plug and play, or was that Allscene? One of those two groups. I think it was IoTivity. We then also have, in this case for Thread, they're going to use MDNS. So this is also known as the Apple Bonjour protocol for those of you who are Apple fans. MDNS has pretty much become a standard. It's one of the typical 224.0.0.251 addresses or something along those lines. So it is a fairly well accepted standard. Microsoft supports it, Apple supports it, Linux supports it with Avahi. So it is a nice example of how we can actually move things around. Now, there are another of options that are available to us that sit on top of that, and one of them, of course, is going to be Zigbee Smart Energy. With Zigbee and the Zigbee Alliance porting their cluster library over to Thread means that we'll be able to take existing Zigbee code and we should be able to port it to Thread with a minimum of hassle. Of course, CoAP and a lot of the smart objects. When we talk about IoT protocols, we have to understand that a lot of these devices that we're dealing with at the edge, they may be Cortex M0, M0+, maybe M3s. We're talking about devices that have kbytes worth of memory, not megabytes worth of memory. A Cortex M0 might have 32 kbytes worth of RAM and maybe 128 kbytes worth of flash. That's it. No Linux, no MMU. You're not going to be doing any of that kind of stuff in one of those types of devices. So we need to make sure that we have the ability to pass as much data as we can without having to spend multiple frames to try and transmit. Remember, every time we turn on the radio, we're going to be draining our battery. So the fewer number of transmissions that I have to make in order to get the communications from the edge device to the border router, the better. And so in this particular example, what we'd end up doing is rather than using RESTful protocols, which are all basically ASCII text, or one of the other protocols that uses XML like XMPP, CoAP, on the other hand, is a binary protocol. So you would have an argument there for using a messaging protocol like CoAP or MQTT sitting on top of all of this in order to pass data back and forth. So what exactly is 6-LoWPAN? 6-LoWPAN has actually been around for a fair amount of time. It's been around for several years now. It is IPv6 over low power wireless personal area networks. That's what it stands for. There is an RFC associated with this, RFC 6282. And basically what they do is they take the encapsulation of the IPv6 header, and then they go through a header compression project, a header compression stage that then shrinks the size of the header down to something much more reasonable. So it enables us to be able to transmit IPv6 compatible packets in very small maximum transfer unit sizes, like we have with the 127 byte 802.15.4 frames. So why did they pick IPv6? This is one of those characteristics that we have to understand. Some of the hype that goes with the IoT is that you should be able to communicate with the cloud, that your devices should be able to talk to the cloud. And the cloud, of course, is setting out on the internet with a capital I, and that means that somehow we have to run IP protocols to get there. The reality of that is that if you actually have your devices talk all the way to the cloud, it means that now all of your devices present an interesting attack surface, because now they're visible from the internet. That's not necessarily a good idea, and that's one of the reasons why we have this other model called the fog model, which then uses the border gateway to encapsulate and basically do the data reduction at the border gateway, and then the border gateway communicates with the cloud. But the reality is, when you're talking about consumer electronics equipment, there really isn't a whole lot of requirement to talk all the way to the cloud. The only reason that you would ever talk to the cloud in this kind of a model is if you wanted to be able to have a smartphone located someplace else control the doors, the lights, whatever. So it certainly is a possibility where we might have a requirement for it, but the requirement for IPv6 here is just largely because we've exhausted the v4 address space. If you took a look at what was happening with ARIN, the North American Internet Registry, Aaron, last summer, put IPv4 addresses on allocation. That means there are no more IPv4 addresses, and you can stand in line to say if you can get one of them. They'll be happy to give you an IPv6 address, however. This picture actually was taken on the day that we ran out of IPv4 addresses. Actually, we technically ran out in April 15th of 2011. Now, did the internet stop? No, it didn't stop. The internet kept on going. But what we're seeing at this point is a significant acceptance of IPv6 in virtually every country in the world except the United States, as it turns out. We see that 95% of all French websites are accessible with IPv6 addresses. Over 35% of all of China's web traffic is all IPv6. China has 6 major multi-gigabit per second fiber optic networks that are all running IPv6. In fact, the 2008 Olympics was transmitted in IPv6. So IPv6 has been out there for a while. It's not a new protocol. It was actually, the RFC for IPv6 was published in 1998. So when people talk about IPv6 being a brand new protocol, if you consider 1998 a brand new protocol, then I guess it is. But in those kinds of time frames, we are just now starting to accept the use of IPv6, largely because now we're being forced to. Since we don't have IPv4 addresses to hand out to anybody, and certainly here in the United States, we had more IPv4 addresses than anybody else, so it didn't impact us quite as much as it did other places in the world, especially Asia. However, if you do happen to have your Android phone rooted, and you can get out to the command line and do a netstat in the command line, you'll actually see that all the addresses there are actually IPv6 addresses. They are mapped, IPv6 mapped IPv4 addresses. So you'll all see there'll be a : FFFF : 192.168, whatever. That's an IPv6 mapped IPv4 address. So the carriers, the actual cell phone carriers, switched to IPv6 some time ago. They really didn't have much choice because of the number of cell phones that are out there in the world. As a consequence, it's just now starting to make itself felt here in the United States and at the consumer level. So these v6 addresses, as I said, they're 128-bit addresses. We have a couple of special addresses like : 1, that's the loopback address, otherwise known as 127.0.0.1 in IPv4 world. IPv6 does not support broadcast, so it's not a broadcast style protocol. It is a multicast protocol. Now they do happen to have a special multicast address, which is the all nodes multicast, which looks a lot like a broadcast, but nonetheless, they don't actually use the typical Ethernet broadcast style mechanisms. The link local addresses for IPv6, if you have a MAC address, an Ethernet MAC address, they have a way of taking a 48-bit MAC address and making it an EUI64 address. Basically, they just copy the bytes down, they stick FFFE in the middle of it, and then they complement the second bit on the high order octet, which then becomes 5E instead of 5C. This is a real simple, if you've got a MAC address, I can make you an IPv6 address, but this address will not route. It will not go outside of your local area network segment, which is actually okay for this kind of consumer Internet of Things type application. We can also do auto-assigned addresses. They have a couple of different mechanisms. They have SLAC, which is a stateless auto-configuration protocol, and they have DHCP v6, both stateless and stateful versions. I think there's another presentation that's coming up here at the conference that talks a little bit about IPv6. So if you're interested in what's happening there, it actually has a direct impact on what's happening here with Thread. So v6 is technically easier to route for a router. If we look at what happens with an IPv4 header over here, we can then see that it's a relatively complex header. In the other case, IPv6 is pretty simple in comparison, but the v4 header is only 20 bytes, the v6 header is 40 bytes in its size. So how do we get this world routability of 6LoWPAN in Thread? The way that they do it is through heavy use of IP header compression. If we were to take a look at the typical IEEE 802.15.4 frame, we see our source and destination address here. These are the MAC addresses. So this is the overhead of an 802.15.4 frame. Then we have the overhead of the compressed IP, either UDP and IPv6 header. This one is for local PAN routing only. So if it's in the house, you would use this particular form. We can take the 40-byte IPv6 header and compress it down to 6 bytes and still have all the functionality that we had in the 40-byte header. If we needed to do multicast neighbor discovery and router discovery, then that's only 7 bytes. But if we actually needed to go ahead and then route it out on the internet with a capital I, that only requires 10 bytes to do that. So we have a significant reduction in the amount of overhead, which then allows us to fit inside of an 802.15.4 frame. So the network architecture for Thread is fairly straightforward in the sense that it is a mesh, and the mesh we have various Thread routers. We have an end device, so an end device might be let's say a smoke alarm, and then that end device would then find its nearest router using router discovery. So it would actually send out a message that says, hey, are there any routers out here? And whichever routers happen to be close by would answer. So what is a router? Well, a router might be a Nest thermostat. So it turns out if you look inside of the Nest thermostat, and we'll take a look at a teardown of a Nest thermostat here in just a moment, if you look inside that thermostat, you actually find that it is, in fact, well, for all intents and purposes, a BeagleBone Black. It runs Linux. It has both 802.15.4 radios and Wi-Fi radios in it, and it is essentially a router. So we have, as it turns out, the Nest thermostat is actually not just a router, it's actually a border router. So the border router will then be translating between the internal mesh network and Wi-Fi. So we'll see that then the way this thing is set up, the addresses are going to be assigned via DHCP v6. So we'll have inside of the Nest thermostat, we have a DHCP server or other devices that are going to be sitting on Thread. We then have all of our routes maintained with RIP-NG, so there is periodic traffic going between the devices. So this little chit-chat that sets up the routes is actually good. It lets us know that the devices are still alive and well and continuing to work. They can also do things like report how much of battery life they have left. So instead of having your smoke alarms have to replace the 9-volt battery in it every 6 months, which we never do, we then wait for the smoke alarm to start chirping, and then we walk around in our house trying to figure out which one is actually making the noise, and then we replace the battery. In this case, they'd actually have the ability for the device to tell me which one needs to be replaced so that I could then replace it without having to go searching around for it. But what this does is this actually enables some pretty low-cost bridging to other networks. So being able to go from 6LoWPAN and 802.15.4 over to Wi-Fi is pretty easy to do with this particular type of model. This also gives us the ability that we have no single point of failure, so that actually helps reinforce the resilient part of the network that they were trying to do as part of their original standards. So the thread messaging model, I go from my home devices here over to the border router. The border router could be a Wi-Fi access point, and then I'll go either Ethernet or Wi-Fi out to the cloud. If I go out to the cloud, then I can, of course, repeat that down to a smartphone anywhere in the world. If I go Ethernet or Wi-Fi and I'm in the local home, then I can also use a smartphone or a tablet there on the local Wi-Fi segment. So there are, all of the devices use standard socket APIs. So we're using the standard socket calls. Again, that's another one of those standards that they decided to incorporate here. So at least we're not doing anything funky with trying to use some completely different messaging technique. It's all sockets. All happens to be UDP sockets. The security side of it, the user is going to authorize the device on the network using the GUI-ful interface. So whether that's his smartphone or his tablet, what have you, his local computer, he will, in fact, authorize the device. Now, that means there's going to be a MAC address associated with this device, and that MAC address will then have to be accepted into the network as part of the normal network setup. The security session then gets established between the new device and the commissioning device to authenticate it. Once the device is authenticated, the commissioning is complete, then the device attaches to the network, and now it's part of the PAN. So we do have to go through this process of provisioning the device onto the network to make sure that it is, in fact, an authorized device. If we don't do that, then basically the device won't be able to come into the PAN, and if it can't come into the PAN, then it can't talk to the other devices, and therefore is not a fully functioning member in the thread type of network. Link encryption is going to be used for all of the messages. So the radios themselves that do link encryption, and then they use DTLS at the application level. So if we happen to have radios that don't support link encryption, then the DTLS will handle the encryption for us. If we have radios that do link encryption, then we have the option of either using DTLS or not, depending on the application that we're trying to accomplish. Encryption, one of the downsides of encryption is you can't encrypt random data. If you try to encrypt random data, it actually expands. So we need to make sure that the data is compressible in some way before we try to do any encryption to it. Therefore, trying to encrypt data on the link encryption that was already encrypted with DTLS would be a bad decision. So we need to kind of make our decisions here. Are we going to use DTLS for the encryption end-to-end? Are we going to use link encryption for the radios? It all depends on the particular application. Of course, since Thread is an industry consortium, their focus is making sure that everything gets through the certification process. By the time you get the Thread logo on your box, you have already submitted your equipment to a testing laboratory. The testing laboratory has operated a whole bunch of different tests to make sure that it is in fact compliant with the Thread standard, and then it will get the little logo on there. So the certification program actually launched in the first half of 2015. It is currently underway. They're still trying to work out some of the details on this. So we haven't seen a whole lot of products at this point that have the Thread logo on them. We know that Nest and Big Ass Fans and several others actually are compatible with Thread, but it's not like you can walk into Best Buy at this point and see racks of equipment that all has Thread logos on it yet. That hasn't happened yet. But they actually published a specification in June of last year. Unfortunately, that specification was only available to members. And that's pretty much where we are right now with Thread. If you're a member, you have access to information. If you're not a member, we're still sitting out here on the outside trying to figure out what it does. Here's an example of a teardown of a Nest thermostat, just to kind of give you an idea of what we mean when we say it's a border router. It runs 2637 kernel. It's got BusyBox and lots of other GNU-related code to it. It's using the effective, it's got an AM3703, which is a Cetera part, it's Cortex A8. So again, this looks a lot like a BeagleBone Black. 512 megabytes of RAM, 2 gigabytes of flash, and it has radios for 3 different types of communications. It has Bluetooth Low Energy, it has 802.15.4, and it has Wi-Fi built into it. So the device itself is fairly simple from a perspective of all the components. I mean, we see the Texas Instruments part there in the middle in red. That's going to be the main processor. We then see the Texas Instruments power management system over there in the kind of the goldenrod color. We see flash in the blue. We see DRAM up there. Actually, I think the DRAM is the blue and flash is up there in yellow. No, I'm sorry, green. There it is. It's in the green. I'm looking at the part sideways here and it says, yes, okay. This is a pretty straightforward device, and then of course they put the little GUI-like thing on front of it that allows you to see what the temperature is, but it is, for all intents and purposes, just a Linux box. So this is giving them the opportunity to then be able to have the 802.15.4 on one side and Wi-Fi on the other, so they can then communicate with the device that's going to be the controller. So how can you get started with Thread? If you really wanted to go out and start doing something with Thread right now, how do you do it? Well, NXP had a device, had a beta device, a beta system that was put out last year, and it was supposed to have been completed, and then you would be in a real official device as of Consumer Electronics Show this year. That is January 2016. That didn't happen. They missed the date, so they're running a little bit behind. However, Silicon Labs, which is one of the major sponsors of Thread, has a device out called the Mighty Gecko Wireless SoC Starter Kit. This is actually a 3-node Thread network, and it has an ARM Cortex M3 that runs the main processor. It has the main board, so you see the main board, you see the actual radio. The radio portion is up here. We have packet trace. There is a sniffer built into it. There's some starter software. The kit price is $499, so it's not cheap, but at least it gives you an opportunity to start experimenting a little bit with thread. They have a product called Simplicity Studio, which guess what, is Eclipse-based, like almost everybody else's whatever studio, whether it's TI's Code Composer Studio, Simplicity Studio, Atmel's Development Studio. Fill in the whatever studio, and it's probably Eclipse, and sure enough, it is in this case as well. Simplicity Studio, however, and one of the things that I will definitely give Silicon Labs kudos for, they actually have versions for Linux, OS X, and Windows. So it's not just Windows and OS X. They actually thought about putting Linux versions out there. So I'm really happy to see that. So SI Labs, I think there's some SI Labs folks running around here, and there was a couple of other presentations earlier in the session from SI Labs. So if you're interested in talking about the Mighty Gecko, interesting, another piece of this carrier board here, you can replace the radio with other radio units. So if you wanted to go sub-gigahertz, or you wanted to focus on Bluetooth or Zigbee, then the radios can be swapped out, and then you can use whatever type of radio you want to use. So it's not just you buy it for thread and then you're stuck. It's you buy it for thread and then you can do other things with it too. But it is, as I say, $500. So it's definitely not something that most of us as hobbyists would go out and buy. But nonetheless, if we're trying to understand exactly how thread operates, then this is one of the easiest ways of being able to do that. So current status with Linux and 6LoWPAN, there's a great presentation from last year's ELC. Stefan Schmidt from Samsung actually did a very well laid out presentation on the use of Linux and 6LoWPAN. 6LoWPAN and the IP header compression, among other things, are in fact supported. If we were to look at the kernel here, we actually see the 6LoWPAN support here in the kernel. I'm sorry, I can't make the font any bigger. The kernel configurator is what it is. But we see the hop-by-hop header compression, IPv6 header compression, mobility header compression. So we have all of the pieces that we have to have in order to actually make it play nicely with thread. So that's good. The kernel already supports it. This is a 4.2.8 kernel, by the way. I'm sure that it's available in earlier kernels. This just happens to be what I'm using on my machine here. So since thread already runs on Linux, we know it does because the Nest thermostat does it, and it's using this on a 2.6.37 kernel, so it's obviously got some support for thread. With that, we can at least, if we know that the libraries are available for Linux, the question now is how do we get our hands on them as developers? Again, if we're willing to sign up as a thread member, then we can get our hands on them that way. We're just hoping that at some point we're going to be able to have general distribution availability of the thread libraries. By the way, the thread libraries are licensed under Apache software license, ASL v2. So like most of Android and the rest of those platforms, they use the ASL license as a way of avoiding the GPL, because if you were to link with it, if it was GPL code, then the GPL would then somehow convey. So as a consequence, they use ASL as their primary licensing model. So thread is still a work in progress. We have a standards-based approach. It has some high hopes. I mean, I'm really hopeful that since it's using 6LoWPAN, it's using 802.15.4, all of these layer 1, layer 2, layer 3 types of interfaces are kind of a standard across the board. We're just hoping that they will ultimately open things up enough that we'll be able to have more experiment type of kits available for use with thread. They don't appear to be coordinating with any of the other IoT frameworks at this point. The thread folks are kind of doing their own thing, and they believe that they have enough of a consortium there that they'll be able to be successful without having to cooperate with anybody else. Hopefully that will change in the not too distant future. But there are development units available. You can get your hands on them. We will have to prepare at this point for the IoT framework wars, trying to figure out who's going to actually win. Will it be IoTivity? Will it be Allscene? Will it be Thread or some combination thereof? Or will everybody just give up and go with Apple HomeKit? Who knows? So with that, I will open it up for any questions. Good, no questions. All right. So, there's a question. They're running about 4 months behind at this point. So I suspect you won't see anything until mid-year this year maybe, or summer. So probably not until quarter 3.
And the Apple one is still in beta, right?
Apple one's still in beta. You have to have secret handshake and all kinds of other crazy stuff in order to get access to HomeKit. So only manufacturers have that one. So in reality, what Thread is doing is no different than what Apple is doing, in the sense that it's kind of a closed consortium, and if you're a member of the consortium, you get the information. If you're not, then you're just set outside on the outside waiting for something to happen. Any question?
If there's any kind of like Thread developing infrastructure for IoT kits like Edison or the
So the question was, is there a Thread development kit for Edison or one of those other platforms? I haven't seen one yet. If anybody's aware of one for Edison or any of the Quark processors or anything on the Intel side, I'd be really interested. Since it does sit on top of Linux, there's no reason there couldn't be one, but I don't know if, I certainly haven't seen a development kit available that sits on top of that platform yet. Most of the stuff I've seen has all been sitting on top of Cortex M3 and M4 platforms. So much lower level, not really the Linux side, but more focused on the actual radios.
any plans to put in as part of the XDK the extensible development kit from Intel or
That you'd have, the question was, are there any plans to make it part of the SDK that Intel's putting together? And you would have to ask Intel about that. Okay, that's it for me. Thank you very much. Appreciate your time.